Well, not here. Oh. So it's oh yeah, I know. I think she's crying. I thought it was a good joke. Oh, good. What did you do?
Okay. Okay, if you can turn to page 17 in your packet. So this is, we've been doing limit definition of a derivative, which we will come back and review, but we're going to transition over to a much more efficient way of finding a derivative, and that is using power rule. And this is really the for our purposes of this semester, this is really the foundation. Everything that we do is kind of built off of this power rule. So we want to make sure that we're really comfortable with this. This is, and because if we struggle with power rule, then it's just going to impact everything else that we do after. So we're going to spend good amount of time doing power rule, but also because we're going to see it so much that eventually we're gonna be able to get it. So let's start with this. So the first is the constant rule. So we know that we're going to keep saying derivative, but I also want us to understand derivative is just slope. It's a more robust version of slope. It's slope of a curved region, but we can still do derivative of a linear, which is just going to be slope. So if my function is just a constant, then my slope is always, my derivative is always going to be 0. So for instance, let's say f of x equals 5. That's just going to be a horizontal line that goes through a y-intercept of 5. If you look at this line here, what is the slope of this line? Slope is 0. And because that slope is 0, the derivative is also going to be 0. So if f of x equals 5, then f prime of x is going to be equal to 0. So if we just continue replacing that word derivative with slope, I think that will be a nice way for us to connect what we know from algebra into what we're doing here in calculus. So here's power rule. Power rule is for anything that has a degree, any function that has a degree. Now, so if you see here, this constant has degree 0. So we have a special rule for that. We know that's just slope. Slope is 0. If my function is in that form of x to the nth, then the derivative is just n times x to the n minus 1. So what we do is we bring that exponent down in front as a coefficient, and then we subtract 1 from the original exponent value. So if my function is x cubed, then my derivative would be what? If I bring that exponent down and subtract 1, what would that look like? So that 3 comes down, becomes 3x. And then what's my new exponent going to be? Yeah, 3x squared. Yeah. So much more efficient than having to go through a limit definition where we have to plug in and expand and clean up and reevaluate, right? A problem that took 5 minutes before, now we can do in a few seconds. Right. But the flip side is because we can solve our derivatives a lot faster, that also means we can solve a lot more complicated derivatives that we didn't have to worry about with limit definition. So as smooth as power rule can be, it can also be a little messier. And so it's important that we make sure that we apply power rule correctly. And so there's a couple of conditions that needs to be set before we do power rule. So let me go through those conditions. First one is we want to convert all radicals to rational exponents. So if I have square root of x to the 5th, I need to rewrite that as x to the 5/2. It allows us to know what number to bring down, allows us to know what to subtract from. So getting that radical to a rational exponent is a lot easier to see what number we're dealing with in that exponent spot. Next up, bring variable to the numerator before applying power rule. We cannot do power rule if the variable is in the denominator. And last is we want to expand the terms. We need to resolve all parentheses and fractional terms before applying power rule. So if we see any parentheses in the way, we got to expand it, clean everything up, and then we do power rule once everything's cleaned up. Okay, so let's look at some examples here. Some of these require cleanup, some of them don't, but I have examples of each of these three in the following problems. So let's start with the easier one here. Y equals x to the 7th. If I want to find the derivative, there's a lot of different notations for derivatives, so I can call y a y prime. That prime just indicates that it's the derivative level now. So what's y prime going to be equal to? What's the derivative of x to the 7th? Same process as this. What do we do? Yeah, bring the 7 down and then subtract 1 from the exponent. So again, a derivative is just describing how the slope of the original curve is changing at every point. If I plug in a value in for x, I'll get a number, and that number will describe the steepness of the original graph's curve. Next up, g of x equals cube root of x. I first need to rewrite this, right? So so we can see what number we're dealing with. So how can I rewrite this? Cube root of x becomes x to the 1/3, right? So now we're ready for our derivative. G becomes g prime. X to the 1/3. What's power rule there? Okay, 1/3 comes down. What's my new exponent going to be? What happens if I subtract 1 from 1/3? Negative what? Yeah. So I'm going to put a -3/3 as a reminder that when I subtract 1, I have to match the denominator here. So 1/3 minus 1 is same thing as 1/3 minus 3/3. And we can clearly see I just subtract the exponent. The numerators here, 1 minus 3 is -2, so -2/3. So this is my derivative. You know, on the quiz or test, you don't have to write that -3/3 or -1. I'm just showing it right now for visual purposes. Like that's how I was able to get to this new exponent. I'm going to ask us that to clean up the derivative, I do want positive exponents. So once we're at our answer level, I do want us to bring the exponent back down to the denominator if there is a negative exponent. So I'm going to rewrite this as g prime is equal to, that x is right now sitting at the numerator level. I'm going to bring it down to the denominator level, share the same space as that denominator 3. So 1 over 3x to the 2/3. Now, if you want to bring a radical back in, you can. So either one is fine. If you want to leave it as rational, you can. If you want to bring the radical back, you can. Again, you never have to rationalize the denominator. So this is fine. This is fine. Yeah, I'm not going to. I just don't want negative exponents. So if you want to get in either of these forms, that's fine. And on the AP exam, if it's multiple choice, sometimes they would show an answer choice as a rational form. Sometimes they would show the answer choice as a radical form. So as long as we recognize how to go from one form to the next, doesn't really. If it's free response, you can represent your answer in any form. All right, part C, y equals 4 over x to the 5th power. I want to do power rule, but something's out of place. What's out of place? The variable in the denominator. So how can I rewrite it so that my variable is up top? Or x to the what power? Okay, if I want to bring my variable up to the top, that x to the 5th becomes what? X to the negative 5. All right, so anytime I want to switch a variable between numerator and denominator, I can just change the sign, right? But this sign is, I mean, it's showing negative exponent, but this is where we want to be before we apply power rule, because we can only apply power rule if our variable's in the denominator, if it's in the numerator. If it's in the denominator, if we apply power rule, our answer, our derivative is not going to work out. So, so now that we're at the starting line, we can find y prime. What's first? What do we do with that? Negative 5. All right, comes down. So what happens when it comes down? We need to multiply that by what? By the 4, right? So 4 times negative 5 times x to the, what's my new exponent? Yeah, because we got to subtract 1. So sometimes we may look at that 5 and feel like, oh, it's got to go to 4, but it's negative 5. So if we subtract 1 from negative 5, we're going to get negative 6. So what does this clean up to be? Y prime equals what? And then I want the answer with the negative exponent resolved. So what's my final answer going to be? Good. So sometimes we feel like we got to bring everything down along with that x, but it's only the x that's getting impacted by the negative exponent. The negative 20 will stay, and the x comes down. So negative 20 over x to the 6th. This is my derivative. Okay, part D, if you look at part D here, there are multiple terms. It looks like just one big problem, but I want us to just realize that this is really for our power rule purposes. This is really 4 separate problems that are separated by plus or minus. So we'll treat each problem individually, apply a power rule to each, and then after we do that, we can just merge it all together and then call that the derivative. But the issue is that not every term is ready for power rule. So I'm going to keep working on each term until they're all ready, and then apply power rule all at the same time. I think what's feels messier is if you try to find the derivative of one term and then clean up the other, And if not everything is at the same level, then when you go back and double check your answer, you're not going to know what you did. So it does take a little bit of rewriting terms, but I think it's good for organizing our work. Now, 8x to the 2/3. Is this ready for power rule? Do I need to do anything to this? Okay. So 8x to the 2/3, there's no variable in the denominator. There's no radical. There's no parentheses. So this one is good, but I don't want to do the derivative yet. I want to wait until every term is ready. So I'm going to rewrite that term. Okay. What about cube root of x? I can rewrite that as what? Sorry, fifth root of x. X to the 1/5, yeah. And then there's two things that needs to be resolved here. 2 over square root of x. How can I get that written ready for power rule? Right. First off, what can we do with that square root of x? Square root of x is the same thing as what? X to the 1/2. But it's still out of place, so we need to bring that where? Numerator. So that becomes 2x to the, what's my new exponent going to be? -1/2 plus 0.875. So we haven't done any calculus yet. We've just rewritten it so that our calculus step can be applied. So I'm just getting every term up to the starting line. And then my next step is to find the derivative. I can just do the derivative all at once for every term. Okay, so now y prime. Okay. Bring the exponent down, multiply with that coefficient in front. Okay, what's my new exponent going to be? Two-thirds minus 1 is, yeah. We bring down the 1/5. What's my new exponent? Negative 1/5 minus 5/5. Negative what? 4/5. Okay. Okay. Bring down the -1/2. Subtract 1 from the exponent. What's that going to be? Minus or negative 3/2. What about this 0.875? What's going to happen to this? What's the derivative of a constant? 0. Yeah. So think of 0.875 as just some standalone horizontal line, and that horizontal line is just going to zero out because the slope of a horizontal line is always 0. So I'll put a 0 here, but you could just leave it blank and not have anything there. So we have our derivative, and now it's just a cleanup stage. So cleanup, I'm going to try to merge the fractions together, or each individual fraction together. I'm not going to ever ask you to find a common denominator here. So as long as we can separate or clean up each term, we can leave each term separate, resolve the negative exponent, and call that our derivative function. So I'm going to make this 16/3. I'm going to push the x down to the denominator. Okay, let me sneak in a part E here. Let's say I had f of x is equal to x to the 4th over 5. minus square root of x to the 7th. We're going to do power rule here. I do want to point out something about a denominator constant that's under my variable. I think sometimes we look at a denominator and it kind of throws us off because we don't know what to do with that denominator. So if there's a constant in the denominator, we can always push it out in front. I think visually it's easier to look at a number in front of a variable than a number below a variable. So if I want to pull that 5 out in front, what can I call that coefficient? Dividing by 5 is the same thing as what? Multiplying by 1/5. So if I just pull that 5 out as a 1/5 x to the 4th, then it becomes a lot cleaner. It feels like, oh, like just some number. It just happens to be a fraction, rather than looking at this denominator going, what do I do with this number? So I want us to get into a habit of, now if you don't want to do that, that's fine. But I think visually, many students have an easier time looking at a number in front rather than number below under the variable. And next up, this radical students have trouble with in terms of getting into a rational exponent. What is the square root of x to the 7th as a rational exponent? X to the what? 7/2. Yeah. This one gives students trouble because a lot of us want to write it as x to the 1/7, but this is not x to the 1/7. X to the 1/7 would look like this. It would be the 7th root of x, like this. Or I see students, they understand that there's a 2 there, but then they want to read from left to right. So they go x to the 2/7, and this is not also correct. So I just want to, I think every other radical, I don't see students having trouble with, but for some reason, this square root of x to the 5th, square root of x to the 9th, these are the ones that where these mistakes occur more often. So just be aware that there's a 2 there, but we go from right to left. So 7/2, not 2/7 or not 1/7. So now that we have our function, we can find our derivative. Bring that 4 down. Okay, next page. So we know that the derivative function can help us find the slope because it's a slope formula for an ever-changing curve. So let's say we have a function that's 1/x². We're asked to find f prime of 2. This is not, we're not going to do this at the first stage. We have to find f prime of x first. And once we find f prime of x, then we can plug 2 into the derivative function to get the slope. So, but let's get this ready for our derivative because this is not quite ready yet, right? How can I rewrite this to get this ready for power rule? This is really what? X to the -2, yep. So now that we have our function ready, we're going to find f prime of x. Once we have our derivative function, then we can worry about what to do with that 2. So what's the derivative of x to the -2? -2x to the -3. Okay, I'm going to clean this up. And now I can use my slope formula to get my slope value, right? because we know that every x value is changing, but we want to find the specific slope of this curve at 2. So then we can say f prime of 2 equals this becomes -2/8, which can reduce to be -1/4. So whatever this graph looks like, the steepness of the curve at 2 has a slope value of -1/4. And now to put it all together, we're going to write the tangent line equation of the function at x equals 1 for this function. So we're going to get the order pair from the function, get the derivative. From the derivative, we'll get the slope. And then from the slope, we can put it into the point slope form. Okay, so I'm going to find my order pair first. Next up, I'll find my derivative. From my derivative, I can get to my slope. My derivative, just go through power rule. Once I have my derivative, I'll clean that up. Okay, so I have my point. I have my slope. And I can just put into my point slope form. Any questions here? Okay, so example 4, this is a more complicated problem here. If you guys can add a 2 in that denominator, make it 2 root x. So what we're going to do is we're going to do power rule, but every term is connected in ways that makes it difficult for us to do power rule. So what we want to do is we want to separate into individual fractions, clean up each individual fractions, treat each like a separate problem, and then find the derivative using power rule once we get them separated. But right now, these are connected in ways where we can't just do power rule for each term and expect to find the correct derivative. So even though it looks like it's 4 separate problems, it's actually one problem that is connected. We need to separate them first. So I'm going to take steps to clean up. So first thing is I'm going to rewrite all my rational radicals to rational exponents. I'm going to begin to separate them into individual problems. So I'm going to separate into three individual problems. And once I get them separated, then I can treat them on their own. But right now, we can't do power rule as it stands because these are not yet separated. So my first step is just forcing every numerator to see that 2 root x, which I convert to 2x to the 1/2. So just also understand that this problem requires a lot of cleanup. And sometimes if we don't know where we are, sometimes I see students get to the end of the cleanup and they figured, well, that's the answer because I spent so much time working on it. But when in fact, all that cleanup is just to get to the point where you can find the derivative. So make sure where you know where you are because a lot of times I feel like we've done so much work that we can just stop. But the whole purpose here is to get to the point where we can do power rule. So now I want to get the x's up to the top. So we do want to move this as a negative exponent. Another way to think about this is if I have two variables above each other, what can I do with the exponents to merge it together? So if I have a to the m divided by a to the n, that's the same thing as a to the what? Yeah, m minus n. So if I can just subtract the exponents, then I can merge the exponents and have it up to the top. So what's 4 minus 1/2? That's the same thing as what? 8/2 minus 1/2, which is 7/2. And then what's 2 minus 1/2? That's just 3/2, right? And then what's 1/3 minus 1/2? I do need common denominators there. So that's the same thing as x to the 2/6 times x to the negative 3/6, which is x to the negative 1/6. So this is my new starting line. Okay. I pushed the 2 out as a 1/2 because I didn't want to stare at a number below my variable. And then 8/2 minus 1/2 is 7/2. We've merged and we've brought the variable up to the top because we can't do power rule with that variable sitting below. And then 3x squared, I can push that 3/2 as a coefficient. And then this is 2 minus 1/2 is 4/2 minus 1/2, which is 3/2. And then the 4/2 I reduced to be 2. And then 1/3 minus 1/2 is same thing as 2/6 minus 3/6, which is negative 1/6. So now we've gotten from this term, this function, this setup to this, but these are the same things. Okay, so we haven't done anything to change the overall function. All we've done is we've rewritten it so that we can actually apply power rule at this stage. Okay, so let's see if we can apply power rule here. So remember, power rule is bringing the exponent down and then subtracting 1 from the exponent. Bringing the exponent down, subtract 1 from the exponent, bringing this exponent down and subtract 1 from that exponent. Okay, try that. Any questions? I do want to show you a wrong way of doing this, which the reason I want to show this to you is because it shows up a lot. And I'm hoping that by showing it to you, we can avoid doing it this way. So this is what I see some students do. They do clean up every term. But then the misconception is that they think that every term is nicely separated. So they start doing power rule within each part. I mean, this feels easy, but this is not going to get us the right answer. And they say that this is the derivative. Now, if every term was nicely separated, if it was x to the fourth minus 3x squared plus 4x to the 1/3 minus 2x to the 1/2, and there's no connection with division, if everything is nicely separated as plus or minus, then you can find the derivative separately. But because they're connected like this, we can't just jump into power rule when these are connected. We have to spend the time to separate each fraction, clean everything up, and then once we get to this stage, then we can do power rule. But we can't do power rule if terms are above each other. Does that make sense? All right, example 5. We want to find the derivative, but one of the conditions that's required is we need to resolve parentheses. So when parentheses are in the way, we have to expand everything out. So how would you expand this function out so that no parentheses are in the way? Or what would you do first if I wanted to resolve the parentheses? Can I distribute the 3x through? Yeah, I got a FOIL, right? Also, I can't just square the x and the 1 because then I'm missing some parts. So we do want to take care of this piece first, right? That x plus 1, x plus 1. Once we FOIL that out, then we can distribute the 3x through. So just remember order of operations. I know that sometimes we want to distribute 3x through first because it just goes from left to right. But remember, parentheses, next bonus takes priority over multiplication. So this is my cleanup stage. Thank you. So once I'm here, I'm have to expand all that out. I'm not ready for power roll yet. I need to get all my parentheses to go away. So if I distribute that through, and now it's nice and clean. Everything is separated. Now I can do power roll for each term. Oh, I don't know if I talked about a linear term here. 3x. Why does 3x become just 3? 3x is really 3x to what power? Right. It's the first power, right? And then that 1 goes to 0, and that 0 just turns out to be just 3. Another thing about it is if I'm just given y equals 3x, this is basically in slope-intercept form, right? X. And we know that if it's a linear term, that number in front is always the slope. If it was like y equals 3x plus 4, y equals 3x plus 5, it's just that number in front. So that's why if I have a linear term, that variable just goes away. But you can also do power rule and make it bring down the 1, subtract 1 from the exponent. That x is 0 becomes 1, and that becomes 3. All right, your homework. Okay, so let's make sure we can find that. This is page 190 to 193. If you flip over next few pages, page 23, 24, those are your textbook problems in the AP practice. Yeah. And I'll make sure the key is on the website so you guys can check your answers. Tomorrow we'll need to do some more practice with power roll, but then we're gonna move into particle motion. Then Monday product and quotient rule, and then Tuesday review. I am finishing up grading your test. They look pretty good. I will try to get them in. If not, tomorrow I will have them in a grade book by the weekend and give it back to you by Monday. All right, come get your phones.